Welcome to my channel AI Basics with AK. Here we are with another new episode in our season 3 Introduction to Statistics, episode 13 Chi-square test. Let us recap whatever we have seen so far from episode 10 to 12. We have learned about hypothesis testing and forming a hypothesis that we want to test it. And then accordingly, we have seen that there is something called null hypothesis and alternative hypothesis. Just remember that hypothesis is most basic thing that a data scientist should arrive at it whenever he is working on any data. Traditionally, we call something called data mining. It means the people think that, okay, let's do some analysis or data mining concepts like association mining and all. The basic principle of data mining is that you are mining the data to extract some knowledge. Hypothesis testing is one of the basic thing that we need to bridge in the gap between the data and the wisdom that we are going to bring it. So in general, there is a pyramid called DIKW. Ideally, we don't create much wisdom, but what we do is that knowledge. So the statistics, whatever we are going to come up with these important questions, add up to the knowledge, and it is famously called as knowledge discovery. Okay, let's come back. And then there is something called type 1 and type 2 error, because there is a possibility that, okay, whatever we have arrived through statistical analysis, it might be wrong. That's what we have discussed as type 1 and type 2 errors. And then for a numerical data, we have seen something as t-tests for comparing the means. And then accordingly, the p-values and significance levels with, by default, 95%, 90%, alpha value is equal to 0.05, which is the significance level that we have seen it, to arrive whether we can reject the null hypothesis, or is there the current data has no evidence not to reject the null hypothesis. This is so far we have seen in episode 10 and 12. The most importantly, we have seen all these things for the numerical data. To answer the question, something like, is the average height different between groups, or is the average height for a class is maybe 4 feet kind of a thing for a particular grade. Okay, now assume that we have a different kind of data, which is categorical. Whenever there is a categorical, we are having something called as frequencies or proportions or counts. We are not actually computing any means or standard deviations, because that is only possible with numerical data. In categorical data, it is no means, it is actually the raw data, which is counts and frequencies. How do you arrive something similar? How can we apply the hypothesis testing to the categorical data is what we will see in this episode. Beautiful, right? Now, in general, it is called as goodness of fit and test of independence. It's similar thing. It's like one sample and two sample test that we have seen it out. Is that, say for example, the question is that, is the dye fair? Do the customers prefer all flavors equally? Here we have only one categorical value about the dye and about the flavors. And then we want to observe a pattern whether the dye is fair or all flavors are equally preferred by the customers. And then the test 2 is like two samples that we have seen it. Here we want to compare PTV in gender and product preferences. What it means is that, okay, is there any difference in preferences with respect to the gender, that one particular gender prefers one particular category and other gender prefers one particular category. Usually the counts in generally is expected that, okay, it's way much different, but ideally we have to use a chi-square test to establish statistically that it is different. So that's where you will use either the test of independence or the test which is called a goodness of fit. This is most fundamental in any of the comparisons. Okay. So chi-square test, how do you, like in alpha value, we are using g-test, right? For arriving at a significance value, and we call it as alpha is equal to 0.05, which is nothing but a significance value, and depending upon the particular g distribution, we have that critical value. Similarly, for a chi-square distribution, depending upon the degrees of freedom, which I will come back to you, depending upon degrees of freedom, it has a different patterns of chi-square distribution. And then this is the probability density. Usually the probability density, we always keep it as alpha as 0.05. Say for example, here for degrees of freedom of 5 and alpha is equal to 0.05, this would be the chi-square, which is approximately 13. Say for example, if the chi-square we have seen it is 3.88, it means we cannot reject the null hypothesis. So this is in generally an explanation how the chi-square looks. It is usually a right skewed and always positive. It does not have any negative values, which is most fundamentally very important for you to understand. A chi-square distribution, it varies by degrees of freedom. The more degrees of freedom, okay, it becomes little bit more symmetric. What is the degrees of freedom, which I told you, I'll tell it later. What is degrees of freedom? We have seen it that here two different, like test one is goodness of fit and test two is test of independence, right? Let me explain for the goodness of fit for one category. Here we have seen that a dice will be having a 6 sides, right? So when we are actually testing for a die, the degrees of freedom becomes the number of different values that it can have, it which is 6 different faces minus 1. The degrees of freedom becomes minus 1. And the similar thing we have it here, something called number of different, if it is ideally 2 categories, in generally you can tabulate the 2 categories as rows and columns, right? Here it can be category 1 and here it can be category 2. Then it is ideally called as number of different categories, which is rows, say for example, minus 1, okay, into number of here categories, which is maybe columns, minus 1. If there are 5 different the genders here, it can be 2 genders, say 2 minus 1, and number of products, say for example it is 3, it becomes 3 minus 1. So the total degrees of freedom will become 2 into 1, which is 2. Got it? That's how it is arrived. This assume that it is derived in that way. And maybe I'll have in another sessions what is actually a degrees of freedom. Maybe in the next, immediately after this episode, I'll actually make an episode. What is degrees of freedom? Why the people call as degrees of freedom? I think that's one of the most fundamental thing we all has to learn, and which I'll clear it out in the next episode. Okay, let's jump back into the into our current episode, which is chi-square test. You can go through this slide, but put it simple, there is a formula here. Okay, you arrive something called as a chi-square. The larger the chi-square, it means we have evidence against null hypothesis. It means whatever we are trying to test, okay, we can assume that it is true. Now let's go back, okay, and then say for example we want to test whether a die is fair or not. Make sense? And then we have rolled a die 60 times. We have observed, okay, this 8 times, 12 times, 7 times, etc., etc. And ideally, if it is a fair dice, we expect every time it is equal. So accordingly, there is a formula, and then we computed the formula, we got 3.8. But ideally, we have seen that the degrees of freedom is 5, and the critical value for the degrees of freedom of 5 for the chi-square distribution, it has to be 11.0. So since 3.8 is less than 11.7, we failed to reject the null hypothesis, and we cannot claim that the dice, okay, is unfair. Okay, so here we are expecting fair, okay, and we got it as fair. So there is no question that, okay, we can reject the null hypothesis that the dice is fair. So there is no evidence that the dice is unfair, sorry. Similarly, let's do the test 2, which is a chi-square test of independence. You can say that, okay, there is a male and female, and then there are 3 products. Null hypothesis will be these are all independent, there is no association. And then there might be an association if, say for example, a particular product, if there is a gender ratio is a little bit higher. People can look at numbers and arrive at it. If there are large categories and large products, it is always better to statistically arrive whether, okay, is there any statistically is there any preference based on gender and product. Rather than arriving thinking like pure correlation, it is very right to check on the chi-square tests. We arrive at everything here based on the formula, and then we got a value called 2.68. And then based on the degrees of freedom of 2, the critical value is 6. So we failed to reject the null hypothesis. Got it? It means these products are not associated, so these products are independent. So we cannot tell that a particular gender has a high product preference. It can be anything. It can be their individual choice, like anybody can like whatever they are. There is no gender preference. This is a weak association, that's what we have seen it out. Let me just go for a stronger association here. Okay, let me just refresh it. Now you can see that this is a stronger association. By seeing at the graph, you can arrive at it as well. You can see that a female has the lower preference for product A, but a higher preference for product C. But how, this is very simpler, but it's always, whenever there is a large product, it is always better when there are multiple categories to use a chi-square test to tell it statistically that it has an dependence or not. Now let's see some quick real world applications before saying it the closure of this episode. In marketing, that's what we have seen it. Do us all customers buy all the products equally, or one product is dominating? Genetics, do all offsprings match the Mendel's ratio, which is 3:1, is predicted or not? In operations, are defects distributed equally across the shifts, or is one shift producing more errors? Which is mostly very important, because the people, when I worked in the manufacturing department, usually the people say that the third shift produce more errors in that shift. But is it by chance, or statistically is where we have arrived at that point of time, and it is backed by real experience that the people who are coming in the third shift has a lesser experience towards the manufacturing process rather than the people who are coming up in the shift 1 and shift 2. Both, it is backed by the data as well as with the practical cross checks. And and other pieces like in healthcare, HR analytics, and retail, and etc. These are all broadly we can see it out. It's most important because we all go with the law of averages. Instead of going with the law of averages, it just tells a couple of lines of code. Ideally, if you can just pass on the data to Python or R, it just gives you the chi-square test if you want to test it out. Because rather than arriving at it with a law of averages, if you are able to prove it statistically that these particular questions have been proved statistically or not, this becomes a little bit a knowledge base for the company or for the research that we are working on, and we can build on that particular knowledge. And then more knowledge becomes a refined wisdom for any business leader. That's it. And That's it for today's episode. And let's connect back in the next episode. And as promised, the episode 14 will be a detailed on a degrees of freedom. Okay. See you. Bye bye.